Krol. I'm part of Air Mobile and 7 Lab out of Stockholm, Sweden. I have decided to talk about this. That's fairly basic things, like back to basics. We'll see how it works. There's something you know all about, but there's an interesting angle on a couple of things I want to present. So, to begin with, the decibel itself. Well, we know the definition. It's kind of dry here, but I've seen it many times. You've seen it many times. Have you ever wondered why this 10 is there? Why? In front of a logarithm. Well, there's a hint, right? It's a tenth of something else. It's a tenth of a bell. Have you ever thought about it? That's a base unit. Let's use bells instead. No, I'm joking. But basically, you could do this. Everybody standardized on dBs that we even forget about bells. Well, it's actually, it looks like this. You get rid of deci part, and you only have bell, and then your numbers are calculation is very easy. So attenuation would be just a logarithm of P1 over P2. Simple. So 1 order of magnitude is 1 bell higher or lower. Well, I'm not telling you exactly to use it, but that's interesting. I've seen things like mini decibels, sorry. Have anybody seen mini decibels? Some scientific papers. If they really want to talk about small changes, they use mini decibels. And it tells us how much do we like decibels. It's not the mini bell, which would be a nice alternative, actually. It's a percent of a decibel. Really good. Again, I'm not telling you to use it. It's just an interesting look at things. Well, we know it's a 10 logarithm if it's decibels, or it's just a logarithm if it's bell. Then we know those rules of 3 decibels. Just remember that it's by chance. So the 3 decibels is 2 times. It's very close. By 10 times is by definition. So if you have 10 decibels, it's actually 10 times, right? You have 20 decibels, it's 20 times. It's by definition. It's just there. 3 decibels is close enough for most of us. And like this. If you have twice P1 over P2, you're going to end up at 3.01 decibel. Okay, that's just a definition. Let's move on. Where do we use decibels? We use it quite a lot in free space path loss calculations. And again, yet another formula. So we know there's this distance component, there's this frequency component, there's a constant. So let's plot it. Okay? It's a nice straight line. Why? Because I choose a logarithmic scale on x-axis. That's 2.4 gigahertz. It's channel 6, the frequency is. So at 10 meters, it's like, 60 dB loss. And then, because it's 20 logarithm there, so each time you go 10 times the distance, you're going to get 20 dB more, right? So at 1 meter is 40, at 10 meters it's 60, and 100 it's 80. Well, we know that that's just a free space. 100 meters, 80 dB, that's why you have problems doing installation in stadiums, right? Because say plus 10, if that's your output power, minus 80, that's minus 70. And that's at 0 dBi antennas on both ends. So that's well above CCI. Sorry, that's well above, it will cause a CCI. Well, the same thing for 5 gigahertz. And that's obviously 6 dB larger. Have you ever wondered why? I did for a while. And I did some study. And I wanted to share. So let's just start with the basic stuff. Why is it distance dependent? That's easy. I mean, it's kind of intuitive. The further away from the access point or the source you are, then it's kind of weaker. Well, yes. So the energy spreads into a sphere, and the area of the sphere is then growing. And then the same amount of energy has to cover larger sphere. And that's nothing new. And then again, yet another formula. The surface area is like this, and we know it's going to give us in signal strength, our SSI value is inversely proportional to R squared. Nothing new at all. So 2R, twice the distance, will give you 6 dB less. We know that. And half the distance will give you plus 6 dB. So that's the easy part. We kind of get it. That's kind of an energy-based part. You know, if you have the energy, why frequency then? Why? Well, an interesting part here actually is we're talking about spreading the energy. There's no absorption whatsoever. If you could, at any given time, aggregate all this energy, add it up on this sphere, you would end up with the same energy as it was in the beginning. So we do not lose anything. It just gets spread out, right? That's the model. Why the frequency? That's the tougher part, right? So we assume an isotropic antenna at the far end, which has an aperture or an effective area, which is a function of frequency. What does that mean, really? We have the area here, and that area is not constant. So if you go up with the frequency, the aperture is actually going down, and it's proportional to f square. So what happens is you tap into a smaller part of this sphere. So that's why you're getting less. It's actually, if you take an aperture for formula for the isotropic antenna, you end up doing this. So that's why your aperture for isotropic antenna is this, and then it would be more or less a quarter of it for 5 gigahertz, if that's 2.4. So you're basically covering a smaller part of that sphere. So the actual energy distribution is exactly the same. It's just that you're getting a smaller fraction of it. So I don't really like this to be called loss, really, but there's no better name for it. It's signal drop or whatever. But then again, if this is the case, how about same aperture antenna? How about we figure out an antenna that has the same aperture, like in square meters, square feet? That should be frequency independent. Let's see. All right, I found that dish antennas are like this, obviously. Let's just assume 100% efficiency, so the area is the area. The area is the aperture, right? Let's do some calculations. This is our old formula. We have 20 logarithms of, sorry, that's the gain for the antenna, for the aperture antenna without efficiency component, so it's just 100% efficiency. And now, free space path loss with parabolic antenna. That's the old formula, 20 logs from distance, and then you have frequency component, then you have a constant. But now you're adding, actually, because that's a negative, that's a gain, so it's a negative loss. So you're subtracting the part from the dish antenna. You see, and what happens now? They cancel out. You don't have a frequency component anymore. It's just a distance component. You're going to say, hey, hold your horses. That's. I know that works. It's sort of worse on 5 gigahertz. And it is. There's a lot of other components. But if you manage to have the same aperture antenna, which would mean roughly 6 dB gain over the in terms of dBi, you would then have the same free space loss. Okay, let's move on, because I look at the clock and I'm getting nervous. RSSI values. So what do we get? Say we take an example, 2.4 gig in this case, output power 10 dB, 0 dB antenna. Well, you've seen it many times. It's kind of very steep at the beginning, and it's kind of plateau to the right. All right? 5 gig there. Have you ever looked at the slope of this? Why am I saying slope? That means more or less at the 1 meter distance, if you differ your position by 1 meter, you're going to get 8.7 dB, lower signal. So it's very steep, right? Or like this. Then 3 meters, 2.9. Then at 10 meters, 87, and so on and so forth. RTLS. This is what if you look at positioning, if you say wanted to have 1 meter accuracy, you should only deal with 8.7 dB would be the difference over 1 meter. If you're 1 meter close, easy to do it. But if you want to do positioning it far out at 100 meters, you need extreme accuracy. 9 millibels, right? All right, I need to go really fast. So, air versus free space loss. I get asked that a lot. How's that? You know, free space is free space. How about air? Well, At our frequencies, nothing happens really. Below 10 gigs, nothing happens. But there, it's 60 gig. Sounds familiar, right? Why? Because that frequency is kind of useless for long-distance links. You have an oxygen-based absorption. The oxygen molecules, they absorb a lot. And that gives you 20 dB extra on top of this free space path loss. So that's useless for them. That's why we got it. We can do frequency reuse. And I'm looking at Rob here and maybe thinking maybe he would like to have 200 per kilometer. That's a kilometer down there. So that's, well, you'd like more to reuse it across the stadium. So that's, again, on top of free space path loss. And we know those, right? And this is the 60 gig. Noise. There's one thing you need to remember. This is this. And I guess you know what that is. Thermal noise spectral density. And that is going to give you the noise power in your channel. Right? So again, if I ask people, where does noise come from? And most of the people say, well, you know, this is interference, there's other networks. How about thermal noise? It's molecules. They have charge, electric charge in most of them anyway. They move and they generate electromagnetic energy. So here's what we got. At 200 kilohertz, it's minus 121 dBm. That's GSM channel. Really nice noise floor. But for us, 20 meg, minus 101. So if you see a noise floor below that, there's something wrong with the measurement. It can only be larger than that, room temperature, that is, obviously. And then if you move on, it's minus 98, 95, and 92 for 160 megahertz channel. And that's just the thermal noise. Best conditions ever. All right? So that's kind of the last slide. Required SNR. That's been discussed a lot. How much SNR do we need in order to get this to work? Well, I took data from Cisco AeroNet 3800, and the values from signal is required signal is from them. The noise is from the previous slide, and the signal to noise is constant. I don't need more signal to noise over wider channels. I need more signal because more noise is already there. You're letting in more noise to your receiver. However, you have to compensate it with signal to keep the same signal to noise ratio. And if you can carry on, I just picked up 2 MCSs. So the same situation happens with MCS7. You're letting in more noise, you're letting in more signal. I mean, you have to in order to keep same energy per beat if some people would like to use that measure. Something to think about, contrary to what many people actually think. All right, so I guess be brave and use Bell. No, don't. The real values, antenna aperture concept, atmospheric absorption doesn't really matter so much now. Thermal noise spectral density, it really is the most important part to understand noise. SNR requirements. I'm a radio amateur myself, so try to calculate as a homework free space loss for 7 megahertz within 1 meter. 7 megahertz, just one of the bands, 40 meter band. You'll end up something very strange, because that's actually far field approximation for the bigger formula. But just do calculations, see what it comes out. All right, thank you. That's it.